So wanting to continue on, we're going to move away from zero-dimensional data now, moving towards one-dimensional data. We're going to start increasing dimensionality throughout this course. We're going to move first from our numbers, taking advantage of what we know about numbers. So you recall from last day that there are important characteristics of our Hindu-Arabic numerals that matter for visualization purposes. The fixed small base, you only have very few numerals to memorize, shapes to learn. And they have positional information, so we have the largest values in the leftmost column, the next largest, and the next to that, et cetera, moving to the smallest values on the right. And line things in columns and, in fact, rows, because these things are standardized height and width pretty much. So it provides a technology for us to do lots of calculation that you've been doing since grade school, various forms of algorithms for doing division and multiplication and subtraction, even finding square roots, etc. So it's easy to use, it's reusable. You don't need very much other than pen and paper or clay tablet, wet clay and a reed to be able to do this kind of calculation. So they're very, very good. So I'm going to begin with trying to take advantage of these things with just a small set of numbers. So what I want from you, I'll just point at you and we'll just go through the rows actually. I want to hear the last two digits of your student number. So we'll begin here, we'll just go up through the middle, if that's okay. So if everybody's paying attention. So could you start with you? 1. Okay. Behind you? 67. 59, 27, 21, 08, 60, keep going faster. Who's next? Wake up. 26, next. No, stay in the middle, just go back and forth. So 43. Yep. 4-6, quicker. 4-8, faster. 2-0. 0-7. 0-5. 5-3. What? Last two numbers. Really? Okay. 7-5. Sorry? 80. Okay, that's probably enough for the illustration. So you notice that I bring these numbers into play. I could start to just order them by their first digit and see what their second digit is. This is stem and leaf plot. So the idea is I've got all of these stems that are identifying each one of these groups. The digits naturally group by 10, right? So it's a very easy, quick and dirty thing to do by hand. That's a first pass sort. I can do a second pass through this, ordering them from smallest to largest. So here's 0, 5, 7, 8, 0, 1, 6, 7, 0, 2, 3, 6, 8, 3, 9, 0, 1, 7, 5, and 0. So now I've got the data completely sorted. A trivial sort I can do by hand immediately. And we can see some sort of patterns in the data. Curiously, in the numbers we've collected, nobody has last two digits beginning with 1 or with 9. Right? If we'd gone through the rest of the class, we likely would have hit these things. But some of these have more in that category than others. Kind of looks like a histogram on its side, right? And it's identified by lining these guys up in the same column. So taking advantage of a standard width for each numeral. So it's a very easy way to get a sense of this distribution, these numbers, okay? And we can do a little more than that. I could start thinking about where's the middle? What's the median value? What's a 25 percentile? If I knew how many numbers were in here, I could just count in from either end very quickly, right? So I could start to count in, knowing that I'm interested in things like, okay, there's nobody there, there's one there, that's the second one, there's 3 more, that's 5. Start from this end, there's 4 there, still 4, 8, okay, this is 7, that's 9. The median's in that group there, and there are 4 of them. These things are called the depth. So with that little bit of a hand arithmetic, I now know how many numbers I've collected, right? I've got 7 plus 9, 16 plus the 4. I also know the median's in here. So I know I've got n equals 20 numbers. So the median is between the 10th and the 11th number. So I've got 9, 10, 11. We can make the median 47. Okay? Is that clear? Very, very easy by hand way to get a quick visualization of a distribution of a collection of digits when you're only looking at 2 significant digits. But now we get some sense of where do they seem to pile up and where are they sparse. Okay, so if I did that for some marks, for example, I'm going to turn off the front lights now. There we go. If I do that for some marks, these are honest marks from Stat 231, some number of years ago. None of your marks are here. Not to worry. And so we can see the grades that were assigned. I don't think you're allowed to assign a grade that low anymore. Okay. Somebody got 16. So you can see immediately you've got an interesting display. You can talk about things like where's the mode, where things pile up the most, what proportion of people pass, right, above a 50, what proportion do not, what proportion in the 90s, etc. And that's done with just this function in base R. How many people have seen stem and leaf plots before? Okay, about a half the class. Okay, so these are very, very handy things that you should have as part of your toolkit, that, especially when you don't have access to a machine. I could change the size of the stem. The first one, when we just looked at that, just back up here, the stem was the first digit alone. Well, however I can divide up 10, I can divide it up into ones like we see here, or I can have it in groups of 5 or groups of 2, right? So in groups of 5, here's this 16's by himself. There's nobody with 20, and here the numbers have got to be 20, 21, 22, 23, 24, because as soon as I hit 25, I'm in the next group. So I've divided by 5 in each group, right? So now we've got a way of choosing the size of those bins that are just proportional as long as it factors 10, which is why it would be nice if we were actually using a base 12 system, because I'd be able to factor, right? But I can have I can split bins of 10 into 2 sets of 5. By that. Some of the characteristics. Why I tell you about this is it's really taking advantage of these Hindu-Arabic numerals and the constant width. We can see a lot of things. We can see 2 significant digits for any. We can see numbers, right? We can see every mark that's there. If those were marks, you'd be able to find where located with relate to the rest of the class. So we can also see the granularity of the data. You can see in this class, pretty much mark seems to be possible. If you only saw the right-hand side, if you only saw 5s, you'd know that I was marking to the nearest 5, right? That's the granularity of the data. So I can see that this is a fairly fine grain that it's down to individual marks. So I even numbers here so that it's not just the even marks. So you can see the individual marks, you can see what is the measurement for this data. So it's still got a lot of detailed information. It provides a sort of the data, so you can get lots of different summary statistics very easily, like the median. It's produced by hand. The other thing is if you squint at it, so that the numbers disappear, you kind of see a density, right? So squint at that and you think that there's sort of a density. That distribution symmetric? No. It's got stretched out on the lower tail and piles up on the right tail on the top end. It's not symmetric. So here's the effect of squinting this. So if I were to reduce this so you only see the gross changes in the spatial density of that figure, you can't see the numbers anymore. What squinting looks like a density, just like that looks like presumably like Marilyn Monroe. Ever know Marilyn Monroe? Okay, on the left. So shrinking is, that whole thing is like squinting. So when you shrink the size of that thing, you don't get to see as much spatial variation. So you get to just see the coarse elements. Now if I zoom in on it, I'll see more details. So zooming in, right, looks like that. And now it doesn't look so much more, but a little bit more like Albert Einstein. It's the same picture. Okay, so when you reduce it, you're only going to see the coarse characteristics of that picture, and when you zoom in, you'll see the fine detail. Leaf plot is you've got both of this happening for you. You can look at details, or you can pull back, squint, and see the pattern, general overall pattern. Okay, so those are the. Make sense? Okay. So depths, like I did on the board there, we can count in from each end. In R, there's a function in the APL package. If you install that package, stem.leaf, which will actually give you the depths. And it constructs the depths exactly as I said. You count in from each side until you're in the middle. And then you just bracket the middle points. So now you know the sample size is the sum of those three numbers. And you know the median's in there somewhere. Okay? So this depth is really, really handy. Now I can calculate a whole bunch of things by hand very quickly. So, particularly, find the median, sort of between the 135th and 136th point. I can find the first quarter the same way, just take the total sample size, find out how far I need to go. Quartile, I'm going to go in from the smallest values, a quarter of the way through the data. Just values a quarter of the way. So you can very quickly get these kinds of values. And things that often interest you are what proportion is below 50 and what proportion above, say, 80%. So there we had, 11% failure rate, 17% above 80. Okay? And that's kind of actually a pretty good distribution for grades. Any questions? That's stem and leaf. And to summarize here, what you could do is you can see the overall density, you can see the details, and with the depth, you can calculate pretty much any proportion in from either end. And that means, probability course, that means you can read off the distribution function. So you don't just have the density, you can actually read off values of the distribution function by choosing the value P that you want to go in to find out what the value is, or alternatively find the value Y and tell me what the proportion is below that. Anything I can do like that. We did that for the proportion below 50. So The key here, I think, is that the values are, and so the question is, maybe, is that enough? Maybe we should just look at ordered values and get. So here's an ordering of heights of the world's leaders at particular time. Winston Churchill's there, Adolf Hitler's there, others. And none of these people are in power now. Oh, Putin, good old Putin. And then we have their heights. And what I've done is sorted the heights from shortest to tallest. And I want you to keep this picture in mind. Okay, so think about you're ordering people from shortest to tallest. If I want to know what's the median height of these world leaders, you don't actually have to measure them all, right? I just have to measure. I just have to measure the two middle guys, which are Winston Churchill and Vladimir Putin, and take their average, which is very convenient. As long as I can order things, I may not have to go the extra effort of actually getting the measurement. I can order stuff. Okay? So the median here turns out to be my present height about. Okay, so I'm roughly in the middle of that group. Hitler, but no, more like sure. Take that, but just putting a dot at every one of their heights. So think about the graph instead of the people being there. Just looking at that plot. That plot should tell us something. And what we're doing is we're taking the height and using the index, the ordered index, as the x value. Okay, so the y value is going to be the height. And so the key here is just sorting the data. As you know, technically the sorted data are sometimes called the order statistic. If you have the order statistic, all the data sorted, you can look up all of these things. You know, what are the third quartile. When things don't work out nicely, we're going to take some measure in between the two values, say, to get the third quartile. So, of course, looking at this in R, the code that we're going to look at, world leaders are here, and I'm just going to get this function here, pp points, getting me the proportions about. There's a slight something that we'll talk about in a minute. And I'm just going to plot the proportions on the x-axis versus the sorted values on the y. And so what I want to look at is that curve. And what is that curve? Well, on this scale, it looks like there's a short guy down here, then a bunch of people that are roughly the same height. There's an increasing in height, and then there's a bunch of people in another group, 3 up here. So you want to look at that thing and be able to interpret what is it telling me about that distribution. Here, piling up. One guy's off on the bottom, sort of outlying, and these other 3 are piling up on the other end. These are all the 6-footers, right? Okay. If I look at the marks, it's the same sort of thing. And again, when I kind of people standing underneath these. Okay? This is called a quantile plot. They're called the quantile. If you look at the marks, when we saw the stem and leaf, what did we notice? It wasn't symmetric, right? There were a lot of stragglers on the low grades. They pulled out, that tail was a little longer. And on the upper side, there was just a little, most of the people piled up towards the upper end. And if you can look at that here, and these are people standing now at the height of their marks. Think about that stem and leaf plot. Okay. From this, you can of course look at, read off any value. If I find the median, what do I have to do? Well, I have to figure out where's 0.5 here, where does it strike this graph, and what mark does that correspond to, right? So just reading that off. This was first invented by Francis, and he was in the 19th century, and he was looking at a World's Fair in London, looking at various measurements on human beings, their grip strength, the height, their sitting height, etc. And here, to have their sitting height measured in London, and he produces this plot. So these are for particular proportions of women. The percentage of women whose height was sitting height was less than or equal to 30 is here. The proportion of women, this is the median, about half of the women in the sample had sitting height, 34 and a bit. So that's their height from the base where they're sitting to the top of it. And it has this nice kind of curve here, so that there's an area in the middle where most of the folks are, and then the top end sort of stretches out a little either end. Francis called this an ogive. This nice kind of S curve. So what he calls an ogive, we now call a quantile plot. And he suggested it because it's so easy to construct. And exactly in the same way you just order the individuals and you measure them, you can go in so many percentage points and find the value. So if you want an idea of where are these people roughly, the 50% point, you just have to find the value of the quantile at p equals 0.5. Right? So that another thing you could do is take a plot, imagine drawing any line on this plot. Segment. Do that in a sec. So you might average percent per n, for averaging the two quartiles, as a measure of where is the center of this group of numbers. And it's simply looking up here from the value 0.5, reading it off. You get the quartiles in the same way, looking at the 25% point and the 75% point. And now you take the average of those two values, the average of the quartiles. It's another measure of where are these values. So comparing these two different measures of location, note that I'm never ever calculating the average. Why? Because it's a nuisance. Calculating the average, the arithmetic mean, is a nuisance. I have to look at all of the numbers. In the median, I just have to look up one number. For the mid quartile, I just have to look up two and average two numbers. Very easy. Okay? In the average, I could also look at this for measures of spread. So the measures of spread, I might think about the interquartile range. That is the difference between the third quartile and the first quartile. It's a sense of how spread out is the data. Right? Go to the first quartile and the third quartile. And that difference, that range, is telling you how spread out the data are. So rather than a standard deviation is also a nuisance to calculate because it's a bunch of sums of all of the data. So I can look at the interquartile range. Historically, half of that was called probable error. You don't see that so much anymore, but you certainly saw that 150 years ago, the probable error would be used in scientific studies all the time. You can think about the spread on either side of the median. So the quartile spread of the third minus the median, or the median minus the quartile, get them the same side. Or any central range for some percentile. Just draw a line and look at the difference in the heights of that line. Okay? So there are the features there. So the spread, interquartile range, is that it's kind of 50% of the data in this plot are between there and there. Okay? So that's showing you the spread of the data. Conversely, you can go and say, I got such and such a mark, I got a 60%. Where do I place in the class? Let's read off 60% and see that I'm in the bottom percent, roughly, of the class. So those are the percentiles. So you can go this way or that way. This way to read off the quantiles, that way read off the percentiles, depending on your interest. So what I'm trying to convince you is that there's a lot of information in this very simple plot of the ordered data. And so by one dimension, I'm thinking here, what is the distribution of numbers in a single dimension, a single set of measurements? So, back to points. So typically what we plot are the pairs, the ordered values, and instead of just I over n, I minus some small fraction over n. The default value is 1/2. But there are other choices that could be made. And from this simple plot, we can get a lot of information about the numbers, right? We can find out where are they roughly located, what's the min, what's the max, what's the median, what's the any quantile we want, or and measures of how spread out the data are by looking at differences between between quantiles p and 1 minus p. Okay, we can also detect a lot more. Questions so far? How many people have seen quantile plots? I didn't say QQ plots. These are not QQ plots. How many people have seen quantile plots? Fewer, what I thought. Okay, so let's look at some data. So here's some data from the R package data sets. And these are air quality measurements, a variety of variates that are being measured. So looking at daily readings of the air quality values for May 1st, 1973 to September 30th, 1973. So the ozone, mean ozone in parts per billion, solar radiation in Langley's, wind, average wind speed in miles per hour at 7 o'clock and 10 o'clock at LaGuardia Airport, temperature maximum daily in degrees Fahrenheit at LaGuardia, month and day, sorry. Okay, so the data are there. And we're just going to do a plot like we did for the others. I'm going to do this for each one of the variates. Okay? So, if I look at solar radiation, so now what I have is that's a cumulative proportion. What would you conclude about this? What do you see here? What would be the location? Where do these measurements in Langley's median value, for example? Looks like somewhere around 200. So you can get that. Would be the spread of these? What would be the interquartile range? So 0.25 is around there. 20. 120. Over this way. I don't know what that is, 260, 270, so 140 is the interquartile range, something like that. What else do you notice? What about the shape? If you were imagining this in the stem and leaf, what would be the shape of this distribution? Any sense of where it piles up? Is it equally spread out everywhere? Sorry? It's equally spread out everywhere? Nearly? And why do you say it's nearly equal? This is close to this straight line. These are scale. Spread out, but not quite so much. Maybe there's something piling up here. Let's continue. What about this one? This is the ozone in parts per billion. Equally spread out? No. Where does it pile up? Go ahead. Towards the end, which end? It's piling up on the right? Is this the right to you? Yeah? Why do you think it's piling up there? What's exponentially increasing though? So you're thinking, think about the density of these numbers. Are there a lot of numbers around 150? No. Are there a lot around 125? No. It's not piling up here. This is important. It's not, the numbers are not piling up there. The curve's going up there exponentially, perhaps. Where is it piling up? It's more down on this end, isn't it? There seem to be a lot of values that are near 10. Okay, so the piling up is in this direction. Okay, got it? So it seems like it's piled up. There's a lot of them on the low end, and then it spreads out on the high end. Okay, it's essentially you'd be able to interpret these plots. Okay, this one, what might you say about this distribution? Any guesses? Yeah? Excellent. So noticed is granularity again, the same kind of granularity we saw in the stem and leaf plot. You could some sort of thing about a lot of variation in the values. That's probably something related to the measuring system, right? So there's a discretization there. There are only so many different kinds of values for the wind speed. Now we know wind speed's a continuous quantity, right? So what's happening is you've got it, the measurement of it is just down to some average, some value that is put to the nearest value of whatever the measuring instrument is. That's why you're seeing discretization. Other things. Are they evenly spread out? Well, if I measure the heights of people here, and I only measure to the nearest foot, right? I'm not going to get very many different values. So so the same thing must be happening in the wind, measurements of the wind, and that's important to see, to understand that the measuring system produced this is only producing discrete values. What about the shape of the distribution? Yeah? Okay. Between the what? Okay, so it looks like, this is weird, better look at this screen, I'm moving the mouse. Right, there's sort of this bump in the middle here, and then it stretches out on the high values, it stretches out on the low values. So it's not evenly distributed across this, right? It's stretched out. Everybody see that? So you're going to look at the shape of these curves. That one, I'll just skip ahead, that's a little more evenly spread out, but still it's got some sort of structure here. There's kind of an S thing happening. So there is a piling up here. You can also see some discretization. Okay, the granularity of the data. Well, that's pretty granular. But that's month. So you will be reassured that the months went from May to September like they said. That's pretty granular and also pretty even, right? Those are the days. Not that interesting, you should see that. All right? So here's a different data set. This is from the mass package. This is the Old Faithful geyser in Yellowstone National Park. And what we have are measurements of the duration of the geyser. How long did the geyser blow? So geysers, everybody knows what a geyser is? Right, good. So how long does this water spout last? Right, so that's the duration of it. Now, what do you make of this? Yeah. Bimodal, why? Yeah, so things really pile up here, right? There's a lot of the times that the thing has erupted, or it's lasted for something around 4 minutes. Also possibly some discretization, you know, whoever's timing this, yeah, that's 4 minutes. But that's what and there's another piling up here. And now there's sparsity in the middle. This is sensing that there's a bump here. If you're looking at the stem and leaf, there's a bump here, a mode here, and another one here. There's bimodality. Okay, 2 modes. So you're looking for this stretching out, that's a thinness, there's not much data there. This is the waiting time between eruptions. Not so much by modality. Still seeing occasionally, you can actually wait a fair time between. Old Faithful is supposed to be erupting, you know, every hour or something. It's old. That's what's faithful, that you can count on when it erupts. But it's clearly the range of the eruptions is quite larger than maybe a tourist brochure would have you believe. Right? So the waiting time between eruptions can range the 25% point from about 60 minutes an hour to the 75% to about 80, I don't know what, 84, 85 minutes. So anywhere from an hour to an hour and a half, let's say. Half the time, half the eruptions, you'll have to wait that long. Okay? And you can think about there seems where that seems to be piling up and where it seems to be flattening. So quantile plots, a lot like stem and leaf plots, in the sense that you can see the granularity of the data, you can see where it concentrates. You know, the concentration is where it seems to be flatter, where it's spread out is where it seems to be stretched out. It looks more vertical, right? And you can see variation in the extremes. What do the two tails, are the tails the same? Or in the one that was one had a very long tail on one side, but was piled up on the other side, was skew. And an S shape, or something close to that, something that's symmetric, sort of mirror symmetric in that way, is indicative of a unimodal symmetric shape. So you might look at concave trough if it's concave up, so it's pointing up. Got to do pointing up that way, right? So it's concave up. It's going to have a shorter left tail and a longer right tail. If it's the other way, it's going to have a longer right tail and longer left tail and a shorter right tail. Okay? So you want to be able to interpret these shapes and think about how they work. Okay? So Galton suggested this is so handy. In fact, we should summarize all distributions with just a few proportions. And he suggested 0.2, 0.09, etc. If we did that for grades, he says don't bother keeping all those numbers. If you had to save a few numbers, just save these 7 numbers, knowing that they correspond to 0.02, 0.09, 0.25, the 3 quartiles, and 0.02 and 0.9 from either end. Okay? So look at that. This is for our final grades of those numbers, and that kind of captures most about the shape. You clearly have lost a lot of information, but often not so much. Particularly not so much if they're all shaped sort of this ogive shape, which is what Galton thought often came up in nature. Okay, so we might replace solar radiation in the park like that and think about what we've lost from going to this summary from that. The ozone, right? Again, it's concave up, so it's this long right tail, short left tail. This nice S shape here, and it's still reflected a little bit here with some irregularity on this wind speed. But you clearly lost all of the granularity, right? You've thrown all of that away. In Old Faithful, you see that something odd is happening here, that there's a pile up down here and a pile up down there. You can still see evidence of the bimodality. Okay? So I think I've talked about all of that. Another thing that you've seen is Tukey's box plot. And Tukey says instead of those 7 numbers, I want to summarize it by about 5 other numbers and draw a picture that corresponds to it. How many people have seen box plots? Anyone not seen a box plot? Excellent. Everybody's seen the box plot. Good. So I'll tell you how they're calculated. They're calculated with from the quartiles, the third and first quartile. That difference is the interquartile range. And then we have to use 1.5 times that to decide what we're going to call outliers or not. And it's important to realize this was all based on small numbers of observations, all to be done by hand. So the box plots generally will find out not that useful without some adjustment for large data sets that we have typically today. So here's the relationship. And this is the language that you need to know. I could imagine I've got the QQ plot here, so these are my final grades in Stat 2, 3, 1. I have the median, right? I have the first quartile and the third quartile. I can just read those off. Then I have the difference between the third and first. That's the interquartile range. Take 1.5 times that, right? Add that to the end of this box, and that's what Tukey calls the upper fence. Take 1.5 times that and subtract it from the lower box, and you get what Tukey calls the lower fence. And then you just look at which one of the values in the data is inside the fence but closest to it. And that's the upper adjacent value, adjacent being beside, right? So that's the upper adjacent value and the lower adjacent value. So now you have the box, which would be the third, second, or median, first quartile. These points that are the lower and upper adjacent values, so you used to call it actually box and whisker plots, is what Tukey called it. And then you just mark anybody that's outside as outliers. So those are our final grades with outliers here outside. And you can kind of see the distribution itself. If you imagine that you're looking at it as an aerial view of the density, it piles up here. 50% of the data are in that box. Okay? And things that are outside here should not show up with that much frequency for low numbers of points if they were normally distributed. So you can look at that and say, what can I see about these various distributions? So things look symmetric if you know if it's symmetric about the median. Symmetric about the median, looking at the two ends of the box or the two whiskers. Are the whiskers about the same length? Are the upper parts and lower parts of the box about the same height? And you get some sense of the symmetry of this distribution. So just from this box plot, I'll be able to talk about the symmetry of this distribution, where it's located, what the spread of the data are. It's kind of like Galton's universal scale summary. In this one, you can see the skewness that we saw here, where it was stretched out this way. The box plot reflects it exactly. So the 50% of the data here, 25% are in that small box, 25% in that larger box, and it stretches out farther up here and much shorter in here. So the whole thing looks skewed. That's like an aerial view of the distribution, and that corresponds exactly to that quantile plot. Okay? So we can look at a bunch of these and see how this quantile plot connects directly with a box plot, and how features in the quantile plot should appear in the box plot, and vice versa. Okay? And there's Old Faithful. Now, what's distressingly missing from a box plot is the interesting feature of this data set is this gap, the bimodality. This plot itself is a model. So this graphic has got a model of the data built into it. And that model is unimodality. You're not going to be able to tell looking at a box plot whether it's bimodal, trimodal, or anything else, because it says I only deal with unimodal data. Right? My model is its unimodal. So that's an interesting thought, that the graphic, the visualization, has got an implicit model. You have to be aware of that. So it's going to miss bimodality that you could pick up in a quantile plot. So as you'll guess by the end of this lecture or next, I'm very much quantile plots over pretty much any of these other graphics, because they reveal a lot of information and they handle large amounts of data very well. So Tukey's box plot, you can see this sort of summary statistics like those universal scale for Galton. You can see symmetry, asymmetric, whether it's symmetric or asymmetric, some outliers, differences in tails. But what you can't see is anything to do with granularity. So you can't see the modes, you can't see how fine is the data, etc. And I remind you again, the box plots as designed originally are for small numbers of data points. Any questions on box plots? Okay, here's another way. So the box is sort of defined, here's a concentration of the data. Okay? The data are concentrated, 50% of them are within that box. Or in the two pieces, there's 25% of the data in each of the pieces. So I'm just going to have a little function here in R that will draw boxes around values that I give it. And I'll look at Old Faithful again. And what you should have realized by now, if not before, the flat spots are where there's concentration. So if I draw from one corner to another corner of this box, with this fixed, decide on whatever width I'm going to have and find that. This out until I've crossed this. That width of that box is telling me how concentrated the data are. Okay? Because that's so wide, there's a lot in that area. Whereas if I put the same width box up here, I'd have very few points. Okay? So if I do that across the whole data set, keep the width of the height of the box fixed, and just see where does it intersect the quantile plot, I'll get different widths where every width is identifying the concentration of the data. Wherever this is wide, there's lots of points. Everybody with me? If I move those to the side, you should recognize that. Right? That's a histogram. That's what a histogram is. That's the connection with a quantile plot. So when you look at quantile plots, you should be able to see everything you can see in a histogram and more. Because the histogram is also hiding concentration details, right? I don't get to see details inside those bins. But everything I can see here, I can see here. Just by how wide is that flat spot of particular height. Yes? What are the what? It's just, they've never changed through this whole thing. That's the proportion. There's Putin in the middle. Churchill's next to him. These are the heights of the people. So that's the grade. The vertical part is the grade that this person got in the course, and they are close to the highest grade. So the highest grade up here was something less than 100 in that course. The lowest grade was this guy that got 16. Okay, so the coordinates have not changed through this whole lecture. And you want to think about stand people up there. Yes? I'm sorry, speak louder. Question. What would you like? Yeah, it's completely arbitrary. I didn't tell you why I chose 10 parts or anything else. But the point is that they're all the same width, right? Other questions? Okay, you can connect these things also to the distribution function then by swapping the axes. And so now I put the final grades in order this way on the horizontal and the cumulative proportion on the vertical. That's the empirical distribution function. That's the distribution function that you're used to, right? And so the empirical's there. But I can do the same thing there on the empirical because if I could turn the screen sideways, we were just looking at that a minute ago. It's just now the fixed width is on the horizontal. I'm looking at the height of these things. So that's why you look at a histogram that way, the connection to the distribution function. And if you think, what's this height telling you? That's the rate of change, isn't it? That's the rate of change, that height over the width. They all have the same width. So the height's telling you the rate of change in the distribution function. What's a rate of change? This is a slope. If I made this instantaneous, it would be a derivative, right? If that was a continuous function. What's a derivative of the distribution function? The density function. What's a histogram estimating? It's a density function. And they're just intimately connected in that way. Okay? So that's pretty much where so what we're going to talk about is this relationship, this quantile function of a proportion. The quantile function is a function of the proportion will give me the y value. It's the inverse of that distribution function, provided everything was continuous and increasing, right? But in the discrete case, we can make this work as well. And that density is that derivative. And all of the graphics correspond exactly to that, those mathematical pieces. Okay? All right, until next day.